At the heart of reality lies a profound contradiction. The fundamental laws of physics, from the classical mechanics of Newton that launch rockets to the stars, to the quantum electrodynamics that describe the dance of light and matter, are time-symmetric. Run their equations forward and a planet orbits a star. Run them backward and the math holds perfectly. The planet simply retraces its path. A wave propagates outward from a stone dropped in a pond. In reverse, the ripples converge flawlessly back to a single point. According to our most trusted descriptions of the universe, the past and future are on equal footing. Yet you and I are prisoners of a one-way street. We remember yesterday, but not tomorrow. We see eggs shatter, but never spontaneously reassemble. We are born, we age, and we die, always in that order. This chasm between the reversible mathematics of the cosmos and the irreversible reality of our experience is one of the deepest mysteries in all of science. What unseen force breaks this perfect symmetry? What cosmic law enforces this relentless forward-only march? The answer is not some exotic new force or undiscovered particle. It is a principle born from the steam and steel of the Industrial Revolution, a concept so powerful it governs everything from black holes to the biology of our own cells. It is the second law of thermodynamics, and it is the universe's most unforgiving tyrant. Formulated by thinkers like Sadi Carnot and Rudolf Clausius, it was initially a practical rule about the limits of heat engines. But in the hands of the brilliant and tragic physicist Ludwig Boltzmann, it became something far more profound. It became a statistical declaration about the nature of existence itself. The second law introduces a quantity called entropy, a measure of disorder, of randomness, of wasted energy. And it makes a single, ironclad statement. In any isolated system, entropy can only increase or stay the same. It never, ever goes down. This isn't a suggestion. It is the bedrock on which our understanding of change is built. This law is why a hot cup of coffee always cools to room temperature, its concentrated thermal energy dissipating into the surrounding air, never the other way around. It's why smoke from a fire billows and spreads, never gathering itself back into the flame. Each of these processes is an act of increasing entropy, of moving from a more ordered, less probable state to a more disordered, more probable one. And here is the crucial insight. This relentless increase in disorder is the very thing that paints the arrow of time onto the canvas of a time-symmetric reality. The past is, by definition, the direction of lower entropy. The future is the direction of higher entropy. They are not the same. But this leads to a chilling implication. If the past is a state of greater order, and the universe is constantly moving towards greater disorder, then every tick of the clock is a tiny act of cosmic forgetting. The universe isn't just moving on from the past, it is actively, physically dismantling it. The information that constituted that past ordered state, the precise arrangement of atoms in an unbroken egg, the specific configuration of heat in a hot coffee, becomes smeared out, diluted across an exponentially larger number of possible configurations. It's the law that declares the past fundamentally unrecoverable. To reverse the process, to unscramble the egg, would require gathering an impossible amount of information about every particle involved and perfectly reversing its trajectory. The universe, in its statistical laziness, simply doesn't bother. It chooses the path of overwhelming probability, the path of chaos. This isn't just a metaphor. The very memories in your brain are exquisitely ordered, low-entropy structures of neurons and chemical signals. The second law is constantly working against them, a relentless pressure that requires your biology to burn energy just to maintain that order. Forgetting, in a very real sense, is you succumbing to the universe's default state. So we are left with a universe whose fundamental rulebook has no preference for direction, yet is governed by an overarching statistical law that screams forward. This tyrant has dictated the flow of our lives, the evolution of stars, and the expansion of the cosmos itself. But how does this statistical tendency gain such absolute power? What is the deep quantum mechanism behind this march toward disorder, and where is it all leading? Building on that profound paradox of an irreversible universe, we must now confront the engine of this change head-on. The second law's power comes not from a force, but from a number, a truly colossal number. The secret lies in the work of Ludwig Boltzmann, who connected the macroscopic world of heat and disorder to the microscopic realm of atoms. He realized that for any large-scale state, like a glass of water with an ice cube in it, there is a staggering number of ways the individual water molecules could be arranged to produce that same state. This number, what physicists call the number of microstates, is the key. Entropy, Boltzmann showed, is essentially a measure of this number. A state of low entropy, like a perfectly ordered crystal or an intact glass, is one with relatively few possible microscopic arrangements. It's specific, it's special. A state of high entropy, like a cloud of steam or a pile of shattered glass, is one with an astronomical number of possible arrangements. It's generic, it's messy. The universe doesn't have a preference for messiness. It just stumbles into it because there are exponentially more ways to be messy than to be neat. Think of it like shuffling a new deck of cards. It starts in a perfectly ordered state, ace to king for every suit. There is only one way for it to be in that perfect order. Now, shuffle it. The chances of it returning to that perfect order are 1 in 8 times 10 to the 67th power, a number so vast it's greater than the number of atoms in our galaxy. The deck will almost certainly land in a disordered, random-looking state, not because of a force of chaos, but because there are countless trillions of ways for it to be disordered and only one way for it to be perfectly ordered. The second law is this principle applied to every atom and photon in the cosmos. It's a law of probability elevated to the status of certainty. This irreversible drive towards disorder is the engine that defines the arrow of time. It's why processes happen in one direction. Systems evolve from less probable states to more probable ones. And this statistical arrow points all the way back to the beginning of everything. The ultimate cosmic question then becomes, if the universe is always running down, becoming more disordered, then it must have started in a state of unbelievable order. And according to data from probes like NASA's WMAP and ESA's Planck satellite, it did. The cosmic microwave background, the afterglow of the Big Bang, shows us a universe that was incredibly smooth and uniform 13.8 billion years ago. This might sound chaotic, but in a universe governed by gravity, uniformity is the lowest possible gravitational entropy. Gravity pulls things together, so a smooth state is highly unstable and ordered, like a pencil balanced on its tip. A clumpy universe full of stars, galaxies, and black holes is actually a much higher state of gravitational entropy. The formation of every star you see in the night sky was an act that increased the total entropy of the universe, radiating immense heat and light into the void as it forged a small pocket of complex matter. Life itself, including us, is a temporary, localized eddy of astonishingly low entropy. We are intricate structures that maintain our order by consuming low-entropy energy from the sun, from food, and excreting high-entropy waste heat. We are, in the words of physicist Erwin Schrödinger, systems that feed on negative entropy. But this process cannot last forever. The second law is patient, and it is absolute. The stars will eventually burn out, their fuel exhausted. According to our best cosmological models, the universe will continue to expand, cool, and darken. Protons themselves may decay over unimaginable timescales, dissolving matter into a thin soup of radiation. And finally, even the supermassive black holes at the centers of dead galaxies will slowly evaporate over trillions of years through Hawking radiation. The ultimate fate of the universe is a state known as the heat death, a vast, cold, dark emptiness where energy is so uniformly distributed that no work can be done. No change is possible. No structures can exist. A state of maximum final entropy. Time itself will lose all meaning, for there will be no change to mark its passage. We exist in the brilliant, fleeting cosmic afternoon, a glorious but temporary phase between the ordered dawn of the Big Bang and the eternal, disordered twilight to come. Our existence is a brief, beautiful rebellion against the universe's inexorable slide into chaos.